Okay friends, welcome back. So we were dealing with propagator theories. Now there are certain properties of this propagator theory, the way we are deriving and everything, and in many places I am not going through the full details of the calculation, but I am trying to give you the flavor of the calculations, and I expect you to go through these textbooks and everything which I have listed in the course to go through the detailed calculations. But it is important for our applications that the end result should be known, essentially the end result should be known, but the technique should be known. So you should remember the technique and how the end result and at least the end result essentially. So we were looking at the electromagnetic propagator essentially, or the photon propagator. Now if you remember okay, so before that we started with the Poisson equation, and then we solved the Green's functions method for the Poisson's equations and derived the same thing essentially here, and showed that it has a form which is 1 by k square, okay, which has a form which is 1 by k square in the momentum space. You see that it has a form in the momentum space which is, but the Poisson is in the electromagnetic equation is exactly the same thing, because of the Laplacian it picks up 2 k squares in the momentum space, and it will be the same thing even in now even if you take the this is electromagnetism, so this is the same thing essentially. So if you take a delta function source and then put in, solve the Poisson's equations, and you get the 1 by k square term essentially, okay, the k square, okay, and this can be represented in the positions basis in terms of 1 by x minus x bar, 1 by r essentially. 1 by r is nothing but 1 by k square in the momentum space essentially, 1 by k square in the momentum space. This just becomes 1 by r Green's function in the position space, but it is always important to remember the momentum space representation, which is 1 by k square essentially. Now in the relativistic k, if you solve for the same thing, the same procedure if you do, but if you do it in terms of the Einstein indices, you end up having eta mu nu also, because there is an a mu sitting here. If you do the same thing with a mu, you need to put in a g mu here, a g mu here, and you end up having an eta mu nu on the top essentially. Because the Green's function is okay, I should not put this one. The Green's function will end up it is a 2 component, it is a 2 point correlation function between 2 A fields essentially, and then you will end up having an eta mu nu picking up the indices of both the things essentially, on both sides essentially. So you will end up having an eta mu nu. I will not go into the details of it, but you should remember that the Green's functions for the amplitude for the photon propagator is nothing but eta mu nu by k square plus by epsilon square. This can be seen in other ways also, but anyway. Now you can do the same thing for the Klein-Gordon field. In the Klein-Gordon field, you have box plus m square phi of x, that is equal to delta power 4 x minus x prime. The Klein-Gordon equation is equal to, now what I want to solve is that this will become the Green's function Again, how do you get the Green's function? I introduce a delta function source, it is a free particle, it is a delta function source, okay, a free particle equation with the delta function source, and then this gives me the Klein Gordon equation. This is also very straightforward to do in the same fashion. G of x prime in momentum in position space, okay, and then this in momentum space Gp, which is easier to remember. Only difference is that, like in the case of the electromagnetic case, the k in the previous case was k bar square, this is k square. In the electromagnetic square, this is k mu k square. In this case, there is a 1 by k square term, that should be a k bar square. Where is this? This is k bar square essentially. So, where I have absorbed the E part into the P part essentially, and then this just becomes P mu P square, this is nothing but P bar square. Here it is P bar square. So, what we have is that the propagator, Klein Gordon propagator, is given by this is the important solution we have got. Okay. Now, before going into deriving the Dirac propagator, so all the propagators are derived in the same fashion. Okay, all the propagators, the steps involved in the solving the propagators are nothing but to just to revise, write this equation of motion with a delta function source. Okay, the steps involved. Motion with delta function source, expand LHS wave function in Fourier modes, expand delta function or express, okay, on RHS in momentum space or Fourier case, Fourier mode. This is also, this will become momentum space. Put them back, put 2 and 3 back in 1 and extract the propagator in momentum space. Now there are, okay, this is a general method involved, okay, this is a general method involved for deriving for a propagator essentially, but there are using Green's functions method essentially, you can use Green's functions methods. Now this is not covered in any of the QFT courses, okay, this is not covered in any of the QFT courses. If you where in QFT courses what you do is that is the reason why I wanted to have a special course on this, because these things are not covered in many regular quantum field theory courses, because in regular quantum field theory courses you are taught to derive the propagator either by solving by canonical quantization, either by canonical quantization the field and then putting it back and then computing the 2-point correlation functions, time order 2 point and so on, so or by using path integral methods. These are the two methods which we use typically to solve to derive the propagators in quantum field theory. But what we are doing right now is we do not have to use the full technology of quantum field theory, but we can what I am providing is an alternative method to do the basic calculations without actually going into the detail of the full quantum field theory, and this is the basis. This is the basis for all the calculations, because you see that if you want to do a simple calculation you do not have to do you do not have to know the full quantum field theory technology, okay. Okay, now let me write some important properties of the propagator, okay. And this is the reason why all if you look at any particle physics books essentially which have only tree level diagrams like Helson and Martin or Griffiths or something, you can actually start doing basic calculations, and even experimentalists can do these calculations without knowing full quantum field theory technology essentially. I am not saying it is not important, because at higher and higher precision, okay, if you want to get a rough idea meaning of the experiments what you are doing, even experimentalists, they do not need to know the full quantum field theory technology essentially. You need what I mentioned in this lectures, the relativistic quantum field theory, and that is sufficient to calculate everything, all the 2 to 2 process, simple process, multi-loop process. If you want to go to higher and higher precision where you need to do second order perturbation theory, compute the loops and so on, so now that is the one where it becomes a problem essentially, where it becomes an issue that you need the full technology of the quantum field theory essentially. So some properties of the propagators, essentially that propagators only depend upon distance between the 2 point as long as theory is translation. So in position space the propagators I have written are like something like x minus x 0, okay, So they only depend upon the difference between the 2 points or the distance between the 2 points. So it's obvious that the propagator in position space only depends upon the distance between these 2 points, essentially x and x0, and this is true as long as the theory is translationally invariant, and so fine, this is one of the properties of the sum. The other solution which I already looked at, the other property is something which you already saw. Sum of all the solutions of the differential operator either it is we have seen it for the case of Nabla square or box square. Essentially we have definitely seen the example of Nabla square, del square, okay, is the propagator. So we have m phi m, so it is outer product, the sum of if m phi m and m are the solutions of the differential operator, whatever it is in the given theory, so they end up being of the sum. This we have already seen this example, I am just repeating it, putting it coherently here. Essentially in a relativistic field theory, that is the reason why this is true, actually why this happens, because the propagator is the solution of all the solutions of only the differential operator. In a relativistic field theory, the propagator is not the solution E square is equal to P square plus M square. The propagator contains solutions which are not on shell. What is on shell? On shell is the time when E square is equal to P square plus M square. That means you solve the you satisfy the energy momentum relation of a relativistic field theory. So these particles, if they do not satisfy the relativistic relation, what are they? Meaning for them E square is not equivalent to P square plus M square, okay. So what are they? These are completely different states, essentially, which are called off shell states, okay. This is because you remember that you put a delta function in source here, essentially. If you put the 0 on the right hand side, okay, if you put 0 on the right hand side, that is exactly the relativistic expression E square is equal to P square plus M square. But instead, okay, you are solving for, so what is the, okay, let me put explain you one more time, essentially that. So you have E square is equal to P square plus M square. Say for example, now you write it in terms of the differential operator del square, del T square, Nabla square, M square, okay. And then if you put it to 0, putting it wave functions on both sides, putting it to 0, then this wave function will always satisfy on shell condition. This wave function will always, like the Klein Gordon solutions or Dirac equation solutions or something, which will always solve this. But the propagator is defined to solve E square minus P square minus M square is equal to delta. So, I put a delta T here and then I put a psi here, nabla square, and I put a G, sorry, instead of psi I should put a G M square G is equal to delta. So, this G need not satisfy E square is equal to P square plus M square. So, G will not satisfy G square is equal to M square plus M square. So, these particles do not have the exact mass and energy which satisfy relativistic particles. So, such particles are called virtual particles. Virtual particles so they do not satisfy the energy momentum dispersion relation. Okay. Virtual particles do not satisfy the energy momentum relation. So, this kind of concepts I think are much better understood and physically much more better understood in a relativistic quantum mechanical setting than in the full field theory setting. Of course, you can do that, I am not against it, but a physical picture you can get in a nicer fashion. So, virtual particles are particles which do not satisfy the energy momentum dispersion relations, but they are short lived, they are not real, they are not physical particles, meaning these particles are not physical. They exist for a short time. So, these also carry momentum and everything, but they exist for a very short time within the uncertainty principle time scales essentially. So, another nomenclature, important nomenclature for you is that to understand that these are something called off shell. E square is not equivalent to P square plus M square. So, these are particles which satisfy they are called off shell, they are not on shell, whereas on shell particles satisfy E square is equal to P square plus M square. Okay, off shell means that they do not satisfy the energy momentum relation, and the reason why they do not satisfy anti particles is that they do not satisfy the is because they contain all possible solutions, including the one which is when delta function, no, you have put in a delta function interaction. So, they are not equivalent to the same essentially. Now, physical experiments can only detect on shell particles. So, in an experiment you can only see a particle which is physical essentially. Okay. Now, virtual particles cannot be detected directly, but their effects can be spelled. Okay. But their effects are felt in precision computations. And if you do something measure very precisely, you need to match it with precision computations, and these virtual particles contribution have to be taken into consideration. Now here also one more thing before going into the next point, essentially I will need to mention one more thing, is that the propagator we are calculating is again in the absence of interactions. We are putting a delta function source, but we are not actually including the interactions in the equations of motion. Essentially you are taking a free particle equation and putting a delta function source and solving it. So that means that the propagator we are calculating is again in the absence of interactions. Okay. So that means an exact propagator is very difficult to calculate. Exact propagator but you can calculate perturbatively corrections to the propagator like what we had done, what I have shown earlier essentially. But corrections can be calculated by adding a step, an interaction at every point, like in time dependent perturbation theory, like similar to time, it is not time dependent perturbation, but similar to time dependent perturbation theory. We can add an interaction at every step, at every point, and then you can expand the series completely. Okay, you can keep expanding this series, and this way you will continue adding corrections to the thing. But what we have seen in most of the examples is that we will know that these corrections are there, okay, but perturbatively one can calculate the corrections to the propagator in the presence of interactions. Okay. So, okay, now these are the general properties of the propagators essentially, and this will keep in mind. But using the propagator theory, a very important thing will comes into the picture, which is called the Feynman-Stackelberg interpretation of so if you look at x and t space time plot of any particle, so a particle travels from here, then here, next travels like this essentially. Now it always travels forward in time because it has to travel forward in time, right? Any particle will always have to travel forward in time. Now the reason I am introducing now this here is because we started using this space time diagrams for propagators, right. Essentially for propagators we are saying that these are Green's functions. So you between space okay, you are traveling, you now do not go backwards in time, you are always traveling forward in time essentially. Okay. Now if there is an electron which is traveling x to x1, x to x prime to x2 and x to x2 prime, that means it is traveling in a sort of sense, essentially it is traveling in a particular way essentially. Okay. Now when the energy is different, when the energy is 0, I mean negative, not 0 essentially, when the energy is negative, what Feynman and Stapelberg was saying was that, okay, now imagine that, so all the lines will always be forward in time essentially, always will be in forward in time. But suppose if you have something like an exotic point like pair production, in a pair production what happens is electron comes in and then in between there is a pair, the positron comes back in, there is a positive charge of the electron, essentially electron which has an opposite charge which is coming. Now so if you look at the charges, so the charges will become a positive charge suddenly and then go back to a negative charge or whatever it is essentially. So this is a situation, this coming back in time is typically what you can find in process like pair production. Now this pair production is because if you plot it with a positron picture, essentially if you are plotting with a positron picture, this will be like x1 and x2 traveling backward in time essentially, x1 to this is, so because this is x and t, if you zoom this one, this is like traveling x1 prime to x2 prime, traveling backward in time. So if you are traveling backward in time with energy negative, so whenever there is a particle, because there is a negative energy particle is produced in the same say space time diagram, it will go backward in time essentially. Okay, it will go backward in time. So because it is negative energy, what Feynman and Stackelberg interpreted as, suppose if you invert it will appear like this, okay, it will appear like this on a space time diagram. So this negative energy particle is like a particle traveling backward in time with negative energy, but with positive energy it will appear as a particle traveling again to the same distances forward in time, okay, with E positive essentially. So at end of each vertices, when there is a creation or annihilation of particle essentially or an absorption of a particle, P will be replaced with minus P, okay, P will be replaced with minus P, or creation or emission of a particle, P will be replaced with the negative sign of P essentially, negative sign of P. Okay. For a particle it will have creation of a particle and particle will be just a p with a momentum p essentially, whereas creation and annihilation of an antiparticle will be with negative energy. So, it will come with minus p essentially, minus p mu. That is the reason why it shifts the sign essentially, why it shifts the sign. So, if you shift the sign essentially, instead of trying back from A to B essentially, so if you go to B to A, this will be equivalent to saying that the particle is antiparticle is travelling backward, positive, forward time essentially. Okay, particles are traveling forward in time, antiparticles are travelling backward in time. Okay, so antiparticles are nothing but particles travelling back in time, okay, with charges reversed. So, the basic point is that particles creation annihilation with p mu whereas antiparticles creation annihilation with minus p mu. So, instead of changing the sign of p mu, keep it p mu positive and change sign of t, because in all the wave functions p mu comes with t essentially. Okay, p mu comes with x mu. Okay, p mu comes with when E changes sign, t also changes sign. So, E changes sign. So, E is negative, t is if t is negative, so E t becomes of same sign essentially. Okay, if t becomes negative, E t becomes same sign as particles. Okay, same sign as particles essentially if t becomes negative. This is the crucial input of Feynman and Stuckelberg, okay, and that this is a crucial expansion. Of course, you can build much more on this essentially, but this is the basic idea that you can always consider particles as antiparticles as particles travelling backward in time, because you are just changing the E sign and the energy sign essentially by changing the t sign essentially. So, but of course, you will say how can something travel backward in time, but that is the antiparticle essentially, that is the antiparticle. So, they become positive energy and so on. So, okay, that is the Feynman-Stuckelberg interpretation, and this will allow us to calculate the basic applications, okay, of simple process without going into the details of full quantum field theory, and we will start doing some simple process and simple process in QED. We are already calling it as QED because it is QED, but it is not fully quantized QED. Essentially, we are not quantizing the electron field, we are not quantizing the photon field and so on. So, at some point I will do it depending upon the time remaining, but we are using all the wave functions and everything essentially. Okay, I will stop here, okay, and then we will continue in the next lecture.